talks. Ladies and gentlemen, welcome to iCANX Talks. Today, I'm a moderator. Alice Zhang was from Peking University. More greetings from Beijing. Actually, it's a spring everywhere, so we're so excited. So this month, we have super speakers on iCANX Talks. So last week we have Jill from Stanford. So today we have Xiaoyu from California, Berkeley. Next week we have CTU, Yu Xinge from CTU. And then we have Lu Yang from the University of Hong Kong. So it will be a big month for everyone to enjoy all these wonderful talks, actually major on the advanced manufacturing. So today's talk, the group was great young group, as me, I'm an older one, but all others are very young, exciting scientists and PhD on this stage. So today's speaker is Xiaoyu Zheng, and we have panelists Zhang Yi and Pan Rui. I will introduce them later. We have a challenger, was Han Xiang from UCLA. So we will get 1 hour talk from Xiaoyu Zheng first. So Professor Xiaoyu, I know him many years. I can say that, right? Yeah. So Xiaoyu was really a pioneer and a superstar in the manufacturing field. So I mean, now he's the director for the advanced manufacturing and Metamaterials labs and UC Berkeley. And he also faculty was a co-director and Berkeley Sensor and Actuator Sensor. I just say that, this BSEC was really nursing many things. Yeah, many leading works. So Xiaoyu did a lot of very significant, contributions in the novel 3D printing technology, metal materials, and it also was, famous for, the function and structure and electronics materials and printing process. So all these are, keywords for Xiaoyu. And his work has been highlighted in many ways, not only in the top journals, also, in the, like MIT Technology Review Top 10 Innovations, LA Times, and many other, social medias. And Xiaoyu got a lot of awards. I can say that few here. So NSFC Career Award, DARPA Young Faculty Award, and DARPA Director Fellowship, and many. Okay, yeah, very famous. So to save some time for Xiaoyu's wonderful talk, so I will stop here. So Xiaoyu, stage is yours, please.
All right, thank you so much, Professor Alice Zhang. Let me share my screen.
Yes, please.
Just make sure everybody can see my screen.
Yes.
Okay, perfect. All right, good morning, everyone. My name is Rayne Zheng. I'm a faculty member at Material Science Engineering Department from UC Berkeley. Today, I'm really glad and honored to be here at this platform to share my research on additive manufacturing and metamaterials. So the topic of my talk is intelligent metamaterial. I want to talk to you about how we can develop additive manufacturing technology and design strategies to design new materials to shape the future of product and material design. So I would like to really give you an overview of my current research focuses in the recent past years. All right, so let me first start by just really basic material properties. So all materials that we use and select for engineering applications are always limited by their raw material property. And they're always limited by the crystal structure, chemical radii, atomic bonds, and that really dictate the material behavior. For example, so metal will always be ductile, and here's the mechanical behaviors of metal. And then ceramic is a very brittle material. So these are the natural material properties that really limit us when selecting different materials for different applications, from structural applications to electronic and robotic applications. So we're really limited by the raw material properties. And as such, we have to follow iterative design and the manufacturing process to manufacture each component and then assemble them into an eventual product. Okay, so what if in the future we don't have to be limited by these limitations? So what if in the future we can start with any desired behaviors or properties that we want? So you can start, for example, by designing a low displacement curve for a material that you want to behave, or a electromagnetic properties that change with time and space, and then leave the rest to computational design, artificial intelligence, and manufacturing processes that output a product that behaves exactly what you want them to behave. So how could that be possible? That really need us to develop manufacturing capability to assemble these three key elements. So the first one is we need to have the ability to assemble materials into any desired three-dimensional topology. And the second element is we want to have this ability to control feature sizes across multiple length scales. And the third and also extremely important element is we want to be able to assemble different functionalities or material classes into that digital platform. And that really comes into the concept of metamaterial. So metamaterial is an engineered material that have properties that go beyond their raw materials. And then you can really define your own properties from these metamaterials. So it really feels like a fabric as a continuum materials, but you can define all these new properties that transcend the limitation of the raw material behavior. For example, there you can have negative thermal expansion coefficient, negative index of fractions, or exotic mechanical behaviors from these materials. So you won't be able to actually see their individual building block because each unit cell is really small. So that's really the overall concept of metamaterial that has been developed in the past, I would say 30 to 40 years. And then, so our work really started with the field of mechanical metamaterials. So this is the work that I developed when I was a postdoc at Lawrence Livermore National Lab. So this was the first mechanical metamaterial that ever been printed. This metamaterial is ultra lightweight. As you can see over here, it weighs about less than 10 kilogram per cubic meter. So what that means, this means it is 100 times lighter than water, but it is able to support weight more than 10,000 times of their own weight, but also being able to have almost zero deformation as compared to a steel foam, which is a steel is a material that is much heavier than these microlattice structure, but already deforms as you show here. So these extreme mechanical behaviors really comes from the internal architecture that we can design at the micro and nanometer length scale. So the individual building block is a micro scale unit cell. We call that stretch dominated mechanical metamaterial unit cell. So it is designed in such a way that no matter how you load it from any directions, all their structural members will only carry axial stresses. That's how you can make a material really stiff. And if you tessellate these micro unit cells, repeat them over, 3 dimensions, and replicate these units over, hundreds to millions of these unit cells together, and that really gives you a metamaterial. And if you can shrink the size of this ligament, especially the wall thickness to, a few microns to tens of nanometers, you can make them really lightweight so that their volume fraction, which is, how many solids, the fraction of solids within the cubic volume can reach less than 1%. So 99% is air and the red, and only 1% is the solid material that carries the weight. And then we show that at much lower density. So this is a density almost similar to carbon aerogel, but you can achieve more than 4 orders of magnitude higher stiffness and strength at ultra low density. So this is really attributed to the stretch dominated microarchitecture being designed and replicated at micro nanometer length scale. Okay, so this is our earlier work, and then we follow up these metamaterial concept to larger length scales and to different materials. So this is an example of a metallic. So this is a nickel metamaterial, And you can look at these microscopic images. You zoom in under optical microscope, and then the row here it shows the scanning electron microscope images. You can see these recurring hierarchical mechanical metamaterial architectures spanning over 7 orders of magnitude in length scale. So with the smallest length scale being a few microns, with feature sizes down to tens of nanometer wall thickness of metal. And then you can see this metamaterial comprised of smaller metamaterial, and each smaller metamaterial block is comprised of an array of these stretch dominated units. So that really collectively give you not only rigidity, but also highly recoverability over multiple cycles. So this is an example of a metamaterial, metallic metamaterial being compressed to over 90% of their own strain, and you don't really see any structured behaviors or plastic behavior of this metamaterial. So unlike when you compress a can of Coke, this metamaterial can always recover no matter which loading direction you give the force. So this is the first demonstration of a ultra stiff but also recoverable metallic metamaterial. So this is really attributed to a collection of stretch dominated design over multiple length scales, and you can actually trigger different buckling load at different length scales. Okay. So I'm sure most of you have heard the exciting talk given by Professor Joseph Dieselman from Stanford last week, a couple of weeks ago, on stereolithography-based technique. So there are all different 3D printing techniques that can make metamaterial. So a light-based technique is one of the most suitable because it can really give you small feature sizes and complex geometry. So this is a technique that we developed when we were at Lawrence Livermore National Lab. So this baseline technique is a projection microstereolithography. So you start with a CAD model, and then you slice this model into digital images. So each image is comprise the cross section of the design, and then you go through a custom design optics and shrink the light into micrometer domain, and then you can get a solid lattice structures within a photosensitive monomer. Okay, so here's a C2 movie showing the process. So you can have both bottom up or top down version of these light-based 3D printing technology. So here's a top-down system where you shine the UV light from the top, and then you can actually use the elevator. So elevator is the stage, and then you just lower it, and you can drag a lattice structures within the liquid. And this one, similar to the clip technology that you see, you can actually lift a solid lattice structures from bottom up. So this is the baseline technique, but also in my lab, we really actively develop different embodiment of the technologies. We really focus on customization of these light-based 3D printing system to make them to process features across multiple length scales, as well as printing material that is highly viscous and functional. So it's one of the key focus in my research group. And also the ability to combine different materials, not only materials with different colors, different mechanical properties, but also materials that may come from different material classes or functionalities. So although the baseline technique can only process polymer, but through advanced material feedstock synthesis or post-processing, you can convert these single material into other materials as well. So here's the polymer, but in that paper, we also show that you can do metal deposition and etch away polymer leaving behind metal lattices, or even graphene metamaterial. So this is an example of a graphene metamaterial that one of my first PhD student, Rayne, demonstrated, where you start with graphene oxide and you print them into a green body, and then you do pyrolysis and burn them into a three-dimensional graphene architecture, where each ligament is comprised of woven graphene sheets. And then you can also do high temperature ceramic. I believe Professor Joseph Dieselman also demonstrated the possibility with clip technology. So you can do silicon oxycarbide, silicon carbide, all different type of high temperature ceramic. So that is the baseline. But we're also very interested in looking at how do you scale up these metamaterials and what will be the eventual property limitations. And from an engineering practice point of view, how can you design metamaterial that have desired failure load or fracture toughness? So this is a really difficult mechanics problem that has been intrigued by multiple mechanics people in the past 50 years. So here's an example of probably the largest metamaterial that has ever been fabricated. So it's a metamaterial that you look at, this look like a cheese box, but it really has more than 10 million unit cells. And then we've been collaborating with Professor Vikram Deshpande from the University of Cambridge, one of the world's best mechanics experts. So we're really interested in studying the fracture behavior of these metamaterials. So it is really important when designing materials with limitations. For example, what are the damage tolerance? If you have a crack inside the materials or any type of defect, how do they behave? So you really need an advanced tool to really visualize these failure modes. So we collaborate with Dr. Vikram Deshpande very closely on really looking at their in situ loading, and then look at how the crack can propagate and what are the failure mode and mechanics laws governing the fracture behavior of this metamaterial, and whether we can define new mechanics and that defines the failure behavior of this material. So here's the XCT image really shows, so we introduced these really thin cracks. So this is embedded flaw that we introduced, and then apply uniaxial or triaxial tensile experiments and look at the failure mode. So long story short, we really observe very different and exotic mechanical behavior that you don't really see in the continuum materials. So one example being these metamaterial, we intentionally made the raw material, which is the base polymer, to be an elastic brittle material. So elastic brittle material is a material when you have a crack, and when you load them, they will fail catastrophically. But what we really observed lately is they really don't fail catastrophically. So they experience an R-curve behavior, which is similar to the bone in our body or a biomaterial. So biomaterial, when they have a flaw and when you try to stretch them, so these plaque will not propagate immediately, but the plaque will actually change its shape and display a really ductile behavior. So we're really intrigued by this study, and then realize you can see that these metamaterials, despite being made out of brittle material, it actually have a very strong ductile behavior, meaning that the crack does not really catastrophically propagate. It actually keep changing its shape and adapt themselves. So this is a new work that we have recently submitted. And the earlier work, we also, our collaborator, Anchor, who is also now a professor at the University of Cambridge, and also my student, Huachen Cui, who has graduated from my group and now assistant professor at Hong Kong University of Science and Technology. We have figured out a design criteria for these types of metamaterials. So eventually, when you scale up from a few microns to meters or tens of meters level, what are the failure criteria governing these mechanical metamaterials? So we come up with a design map and tells you what type of unit cell you need to choose, what are the strut angle and diameters which give you the maximum fracture toughness of these metamaterials. And you see drastically different behavior from a continuum material. So this is an ongoing work, and we're really fascinated by a lot of these intriguing mechanics governing the fracture behavior of these metamaterials. So we can also introduce mesoscale control within these hierarchical metamaterials. For example, you can also introduce carbon fibers. So here's a setup that we have developed that allows you to scale up these metamaterials to meters or meter level with micro scale features with embedded carbon fiber. And recently, my postdoc, Qi Chen, has also achieved the alignment of these microcarbon fibers within these metamaterials so that in each ligament, you can have these fiber to be aligned in 3 dimensions, meaning that all these fibers can be aligned along the axial direction of these trusses so that you can maximize the mechanical properties as well as tailor their anisotropy of stiffness at different loading directions. Okay, so the really benefit of these mechanical metamaterials is the design opportunities. So for researchers who have been investigating mechanical metamaterials, you see that these metamaterials, when you load them, they will have really interesting mechanical behavior, and that mechanical behavior for any materials is displayed by their stress strain curve. And for mechanical metamaterial, with this topology design, you can have really interesting exotic stress strain curves and give you tailorable energy absorption behaviors. So then the question is, with unlimited design possibility across multiple landscapes, how can you actually design them? So the answer is there has been no systematic design technology. Even topology optimization will struggle with designing these nonlinear mechanical behaviors. So we resort to machine learning to design metamaterials. So this is the work that my postdoc Chen Hua has first investigated. So our concept is you start with the designer. So let's say designer is a front-end engineer or a customer. You come up with your design mechanical behavior. So let's say you can draw a stress strain curve, which can be also a force displacement curve of the material behavior you intend to have. And then you input that into a computer algorithm, for example, machine learning code, and then output a metamaterial. So here I just draw a block. So what that means is it can be any design, and then output a design, and then you 3D print them and test them. It can actually replicate intended behavior. So we leave the rest to machine learning development. So currently my postdoc Marco has been leading this project on designing a graphic neural network. So this is a multidisciplinary and multi-university collaboration that I lead with UC Berkeley and UCLA to use graph. So a lot of people have been using graph to represent molecular architecture, but here we actually use these graphs to uniquely represent the geometry and the topology of metamaterials. So here the graph is a really unique mathematical language, and here we find out that you can actually use the node feature and the edge feature of the graph to represent the entire information of metamaterials in terms of their geometry, the topology, even the material and the density of metamaterials. So with graph, you can also you can come up with any random architectures by placing the node and edges, and then iterate them and construct a neural network. Then you can train the surrogate model, and which give you the prediction of these any graph models, and also achieve eventually the inverse design of metamaterials. Here are some of the examples. So we can not only do metamaterial design at low frequency quasi-static response, but also high loading rate, as well as even dynamic properties and acoustic properties. So you can iterate these designs such that it does not only have to be periodic metamaterial, but also metamaterials with any stochastic arrangement. So here I'm just showing some examples of these inverse designs. So basically the idea is we can pretty much design within the property space any shapes that is possible with these metamaterials. So you can define a shape with their linear elastic regime, plastic regime, and post-yielding regime. And then you just draw the curve, and then we can give you the architecture that replicates the design. And then the shaded area basically tells you, okay, there's an uncertainty region comes from the manufacturing error. And here's the example of the baseline metamaterial prediction from the machine learning code. And recently, we've also achieved acoustic design, so which is the metamaterial with certain acoustic band gap. So this is in collaboration with Professor Zheng from Penn State, as well as my collaborator from UCLA. So we adopt the same graph neural network approach, but design these metamaterials so that you can prescribe a band gap curve. Band gap curve really tells you, okay, at certain frequency range, you can either absorb the sound wave or reflect the sound wave. So, and then make them into a noise canceling helmet or structural material that can block certain frequencies of interest. So the idea is the same. You start from these design of a characteristic curve of these material, and then output a structure that replicate the characteristic. Here I also shows you some example of the inverse design and how we can actually use them. So here are the C2 movie shows the mechanical loading of these metamaterials. So basically you can prescribe any curve features, not only to have like a monotonic loading behavior, but also you can have a different peak and valley in terms of their peak stress and energy absorption. So these are metamaterials that with multiple peak and valleys. Here's the metamaterial with one peak value, which is come from a uniform design. Here's a design with a functionally graded metamaterial design that you can have multiple peak and valley. This really gives you the ability to tune the energy absorption behavior. So you can actually use these, apply them to different, helmet, shoe midsole. One application that we have been collaborating with Ford vehicle to design these car bumpers. So most of the car bumpers are actually made from honeycomb architectures. So here we apply them, these honeycomb as a baseline architecture, but tune the gradient of the honeycomb as well as the size using our machine learning code and give you the ability to tailor stress curve. So the idea is the user can test these baseline car bumper, and especially at a high loading rate. So what do you really want to do when the car hitting a pedestrian is with high loading rate is you want to be able to minimize or keep the same strength, the stress, so that you can have minimal stress to be transmitted into the human body, but have really large energy being absorbed by these car bumpers. So here, what you can do is look at the stress strain curve from a baseline design, and then you can just tailor the shapes, then leave the rest to machine learning code, and then output a lattice structures that give you the same strength, but also much higher energy absorption. Okay, so my student Zheng has demonstrated the prototype in our lab. Okay, so that's enough about the structural materials that I want to talk to you about today. Now I want to switch gears a bit to also look at how can we go beyond mechanical metamaterials, structural applications. And this is actually true for additive manufacturing in the past 2 decades. So most additive manufacturing approaches has been focusing on structural materials, metal, polymer, plastics, and ceramic or composite at most. But it is really difficult to combine functional or electronic materials into additive manufacturing. That's because when you use additive manufacturing, you always have to introduce a binder, which is the material that can be shaped. But then that gives you the trade-off of material functional properties. So there's a trade-off between manufacturability and functionality. So we have been in the forefront of developing exotic functional material or electronic materials into the building block and metamaterial. And really, we are excited to explore what happens when you combine different functional materials or electronic material into the three-dimensional architecture of the metamaterial. What are the new design space functional behaviors and even applications that you can derive from this layout. So the first experiment or material that we are looking at is just simply conductive materials or materials that we use in MEMS technologies. So here I want to give you an example of MEMS sensors or two-dimensional material that used to control electromagnetic wave, which is like small-scale antenna that has been traditionally fabricated by clean room lithography. So basically, you start with a silicon wafer, you coat with photoresist, and then you do photolithography, and then you can coat different materials and do etching and leaving behind two-dimensional electronic patterns. And then you can etch away these polymers and give you these materials sitting on a wafer or PCB board. So this technology cannot be really scaled up to 3D. So what could happen if we can actually make a truly three-dimensional devices with conductive material or functional material distributed in any arbitrary three-dimensional orientations? So, so my group has been focusing on these three-dimensional electronic fabrication over the past few years. So it is originally spearheaded by one of my first graduate students, Rayne. So we figured out a way to it's kind of like a deposition technique in 2D, but we adapt them into three-dimensional deposition. So you start with these photopolymer that can be printable, or even direct ink technology, or any printable ink. And then you just combine them with electrostatic charges. So what does the electric charges do? So it can basically be combined into the polymer, and then you can pattern using any regular 3D printing technology, multi-material 3D printing, into a three-dimensional scaffold. So this scaffold is really a three-dimensional assembly of electrostatic charges at each different region. You can have negative charges or positive charges. And then you can use them as a scaffold to attract different material depositions. So here's an example that you can actually use these opposite attraction principle to attract different material plating. So it's eventually a selective volumetric electrolysis depositions. And then you can carry them out with our multi-material platform. And here are the example of these three-dimensional architectures you can do with this technology. For example, this Eiffel Tower, you've probably seen them before from Professor Joseph Salon. But here, what we can have is within this Eiffel Tower, at any location, you can have a different material. So for example, at selected region, you can have a metal layer. Can be any metal, it can be copper, nickel, silver. Example here is a nickel dielectric architecture. This is a joyride architecture where at different, it's an interconnected dielectric material, which is the polymer here, and then the nickel phase, which is give you this interpenetrated inorganic and organic material combination. And here I show these quick movie of this the platform. You start with a 3D printed material that carry these charges, and then you put into a solution. So this is any conventional electrolysis plating solution. And then within a minute, you take it out, and you can get a nice three-dimensional circuit pattern. So this is the interconnect we show at any surfaces with any topological complexity. And then you can do this really fast. It's only happening within a couple minutes. So it's not only compatible with metal, but it can be applicable to other functional materials, oxides, magnetic materials, or some semiconducting materials as well, even carbon nanotubes. To really give you the ability to make these building blocks comprised of different materials. You can tune the conductivity, distribution in 3D, as well as the dielectric constant distribution in 3D. So what this can do, so when you have a alternating dielectric and conductive phases, one immediate application that we have thought about is electromagnetic wave steering, which is the electromagnetic metamaterials or microscale antenna that can operate at gigahertz frequencies. So most of antenna that have been used today in your cell phone for any communication, It's basically used to collect radio waves and then send that radio wave into different directions as you wish. But most of these antenna, our electromagnetic metamaterial, is based on a flat substrate. So you start with a wafer or a PCB board, and then you deposit conductive material traces onto the board. And if you look at the 99%, or between 99 to 90%, is made out of this structural material to support these conductive materials. So only 10%, less than 10%, is responsible for the wave guiding capabilities. So a lot of them are actually quite a ways. So we show that with this three-dimensional multi-material 3D printing of dielectric and conductive material, you can use this technology to print almost any type of antenna structure operating at different frequency. Here, I'm just showing a few examples of this is a transmitter array that is, if you zoom in, you can see this comprised of alternating layer of metal and dielectric polymer arranged in 3D. And you can design these unit cells and use topology optimization to design these unit cells such that they can not only be super lightweight, but also achieve wave guiding capability. There's other antenna examples provided by our collaborators. You can actually see this vertical distribution of dielectric materials and conductive materials, fractal antenna, which has to be fabricated by direct metal printing. But here we show that our technology can virtually print any type of antenna. So it's also possible to do this all metal fractal antenna. As well, antenna architectures that cannot be fabricated by any technology. For example, this complex architecture comprised of copper and dielectric material arranged in any three-dimensional layout, or a horn structure with internal channels used to collect radio waves. So my current postdoc, Dr. Zheng, also has been spearheading the material technology platform for this technology. So we can actually now extend this technology to different materials, going beyond dielectric polymers to metal, but also flexible metal, liquid metal, as well as polymer that can sustain high temperature, as well as selective metal deposition within ceramics as well. So you can make or inorganic materials. For example, the ceramic antenna comprised of a pure PCT ceramic and copper being selectively deposited in 3 dimensions. And he also optimizes technology so we can have really uniform coating. And then these metal, for example, this copper can really achieve near their native copper conductivity. So get really high quality. Here are example of these devices being tested with my collaborator, Professor Xiaoyu, who is a radio wave expert from UCLA. So here is the printed form connected with these transmitter array and use them for wave guiding. So you can guide these radio waves into a desired directions by designing these the patterns of these unit cells. And you see that it can achieve over 90% weight saving compared to conventional PCB approaches. And you can also, of course, make these dielectric materials to be flexible, so you can fold these antenna, make them stretchable for flexible electronic applications. So not only these lattice type structure can also make a bulky antenna. So this is the game horn structure with a everything is basically solid. You can have these copper to be selectively deposited in any surfaces, and you can have really complex channel complex of dielectric and copper phases and use them to collect radio waves. Here's also a recent work of using this platform to make other functional materials. So this is an example of highlight perovskite. This material is a photoluminescence material. So basically all these colors are achieved by this material itself to emit photons, and then you can actually see these material displaying color. So it's basically a natural LED. So this material was developed by Professor Peidong Yang, my colleague at UC Berkeley, my department. So we can actually achieve them for material that display vibrant colors at different frequencies. So this work was recently published. Okay, so that is the two scale that I talked about. So structural materials, conductive materials. What if we can now switch gear and add functional materials? So not only they can have conductivity or electronic behavior, but also have multi-functionality. For example, shape memory alloy or thermoelectric material, piezoelectric material. So in this talk, I'm going to focus on piezoelectric material. So this is one of my favorite materials because I was also a MEMS guy making microelectromechanical devices. So one of the most useful materials for robots, sensors, and actuators is piezoelectric. So it can really convert energy from mechanical to electrical energy and vice versa. They're widely used in your everyday sensors, cell phones, or robots for actuation and sensing applications. So this material, the piezoelectricity, comes from the crystal structure of these piezoelectric. So you really need to have this crystal asymmetry at a nanometer length scale in order to have these dipole moment being aligned in one direction. And then when you apply stresses, it can generate voltages and vice versa. So unfortunately, this material is extremely brittle and hard to be fabricated. And as such, when we use them, we also have to be limited by these base material properties. You will have to make an array of these small piezoelectric discs for different applications, for ultrasonic applications, for sensing, to rely on array. Or if you use them for actuation, because these piezo can only, their contraction and deformation is basically only dictated by the crystal structure, and you really have to design this compliant mechanism to magnify the displacement into different directions. That ends up with a device that is much bulkier and you have really limited degree of freedom to work with them. Yeah. So now we're looking at, okay, what if we can actually introduce these nanocrystal, these piezoelectric materials with three-dimensional architecture, such that you can design architecture that can go beyond these natural crystal behaviors. See, here I showed the example of just a few crystal structure from nature of these piezoelectric crystals. So this is pretty much what you can do with natural piezoelectric materials. So what if in the future we can design any arbitrary piezoelectric crystal tensors? And first, you really need the ability to construct these piezoelectric building blocks into a metamaterial architecture. And then you really need to develop a fabrication printing technique to allow you to do that. So we have been working on this for in the past, at least past 5 years on this technology, which we have figured out a way to make high quality piezoelectric materials. So it started with a large quantity of these PZT nanoparticles, and you functionalize the surface and bind them with UV sensitive monomers, and then make it into a photocurable ink, which is basically a highly concentrated piezoelectric ink with these piezo nanoparticles in between our monomers, UV sensitive monomers, basically serve as a binder. Then you can make your 3D printing technology to print them. So this makes this material really viscous. So give us a lot of challenge to use stereolithography-based system to print them. So we have to come up with a hybrid approach. So which is you have to use a nozzle to squeeze these piezoelectric paste. So it's basically like a toothpaste. You have to squeeze this paste and then use a doctor blade, a brush system to give you a really uniform layer of these piezoelectric colloid, then shine light on top and then make your layer by layer fabrication. So an example shown here are, we also introduced, my student Hao Tian has introduced a liquid phase sintering technique that allows us to prevent these a lot of lead from evaporation. And so here's the example of a post-sintering technique that we have developed that allows you to achieve very high density piezoelectric material post-sintering. Yeah, and combined with the alignment approach that you can do, we also introduce an alignment approach that allows you to align these piezo crystal texture seeds into the material. And after string-guided grain-guided grain growth, you can achieve really high piezoelectric coefficient. Here's among the highest that we have achieved using this 3D printed texture ceramic. So this is really approaching crystal, piezoelectric crystal, and outperforming piezoelectric ceramic that you can even buy commercially. And then you can print them into any shapes and use them for both actuation and sensing applications. So for the rest of the time, I'm going to talk about several energy conversion behavior using these types of metamaterials. The first example I want to talk about is sensing. Sensing is a phenomenon we can use for metamaterial, which is to convert stress, mechanical deformation into electric charges. So with these piezoelectrics, three-dimensional piezoelectric, here's the example we show that if you print them into a cubic dimension, so all these three blocks, they look exactly the same to you, right? So, but it's their internal architecture that we design that differ here. So what we saw here is if you mount electrode on top and bottom surface, and then you apply forces from different directions and just measure the voltage distributions in response to force from different directions, what you observe is that based on the design of this architecture, you can have drastically different voltage pattern for forces coming from different directions. So one is the voltage being positive in one direction, negative in other directions. And this design shows that the voltage is positive in one direction, but all zero in other directions. Or you can achieve voltage to have the same sign. So basically you can achieve program the charge generation of metamaterials in response to forces coming from different directions. So this will have to be achieved by a sensor array in current technology. But with metamaterial, you can just have one material building block and then use them to give you a map of force distribution in 3D, not only the magnitude, but also the directionality of the force. So this is the work that my past student Hua Chen, again, he's also now a professor at the Hong Kong University of Science and Technology, and Zheng, who is also my senior PhD graduate, and developed these flexible piezoelectric metamaterials. So you can tailor these polymer to be really flexible, and then with these piezoelectric and selectively deposited metal, and make them into a wearable structural materials. You can call them a wearable electronics, but I also want to call them a wearable structural materials with functionality. So you can put them into a boxing glove. And you don't want to do that, but my undergraduate student, they work on this as a senior design to make them into a boxing glove. So what they demonstrated is that you put into the boxing glove and you punch somebody in the face, and then you can actually read the real-time distribution of force magnitude along your hand palm, give you the force distribution at every individual pixel from these piezoelectric metamaterials. So recently, my current PhD student, William, also demonstrated self-sensing metamaterial composite. So basically like an artificial fingertip, but he tapped it from different directions. Then you can actually measure the forces. This metamaterial can self-sense the deformation in any direction. You can trace your body shapes when these fingertips is being deformed. So you can actually measure essentially the shear force, the frequency, as well as the normal forces, as well as the entire shape of this metamaterial being deformed. Okay, so that's the sensing, which is the receiving capabilities I want to talk about. Now I want to talk about emission. So emission is basically describe the property of metamaterial to convert electric voltages. So you supply electricity, and then it will emit vibrations. So the vibration can range from different frequencies. One example here is the ultrasound vibrations or all frequency vibrations. So here we actually adapt these technologies. So we've been collaborating with medical doctors at different universities on this technology. So this is an example of a stent. So people use them to insert a stent into a catheter and insert it into the patient. But now we can also introduce piezoelectric materials locally. We can do coatings or print the whole piezoelectrics along each ligament of the stent. And then they can serve dual functions. The first functionality we demonstrate is that it can emit really highly focused ultrasound. For example, if this stent, these are metamaterial stent travel inside of a catheter, it can release focused ultrasound and then allows you to melt the drugs in any locations within the catheter. And because of these high pressure acoustic waves being emitted from these piezoelectric materials, you can melt the drugs in situ, and it can also allows you to have accumulated charge on the stent surface. So we have been doing animal tests. So right now we're doing animal tests of testing how these stents can be used to based on the generated charges to repel a blood clot in patients that have cardiovascular disease. So we have seen really promising success with this technology. We are really excited about the future development. Okay, so now let me talk about not only acoustic frequency generation, but also a low frequency, which is the actuation mode. So we also use them for robotic applications. So again, so this comes from the my earlier slides of these piezoelectric crystal in nature. You really can only have a few existing piezoelectric tensors that is governed by the asymmetry of the natural crystal. So what if we could design our own piezoelectric properties? So what we want to have is to have these artificial crystal building block, any shape in terms of cubic block, but you can have your own tensor. You can design your own tensor in such a way that you don't have to use these complex traditional mechanical design to give you these levering to convert the strength in different degree of freedom. This metamaterial itself will be capable of generating strength in different directions. So this is from the work that my first PhD student, Huachen, demonstrated a few, as well as along with our collaborators, is that we can design these metamaterial topologies such that by arranging the orientation of the piezoactive materials, as well as the passive, the structural phase, which can be the ceramic phase, the structural phase that is non-polarized, and conductive phases to make a three-dimensional metamaterial architecture such that it can display all different tensors that you want to have. So it's essentially an inverse design approach that allows you to tessellate the ligament spatially in 3 dimensions, and you can also tessellate them in different coordinate system and give you a metamaterial building block that can convert strength in different orientations. So I'm not going to talk about the detailed design. If you're interested, you can look into our paper published on 2012. And then this shows that you can achieve all different piezoelectric tensor, which really give you actuation property. So for the same building block shape is a cube. And then if you apply a voltage, it can generate either pure shear or pure twist or combination of deformations in different degree of freedom. And we measure them experimentally. So here's an example. Shows our using laser vibrometer measurement to measure the deformation of these metamaterial blocks. So you can actually trace the surface deformation. For example, for twisting deformation, basically you apply a voltage, the top surface will twist, and the side surface will rub, and you can actually trace the surface deformation using a 2D laser vibrometer to trace the surfaces. For shearing, you can actually see the surface being deflected in different directions. You can also tessellate them, different metamaterial unit cells in 3 dimensions so that you can actually select different motions. So here's our motion that has 6 degree of freedom activations. And then we use them as one example to use them to guide lasers with high precision into a long distance. For example, you can just have this metamaterial to support a micromirror. and then just twist these metamaterials and so that it can guide laser beams over 4 meters with a few micron precision, and you can just program the voltages and then guide the laser beam and draw all different patterns with micrometer resolutions. Okay, so those are the precision manipulation. Now I want to talk about using them as a robotic metamaterials. So this is the concept we coined based on this metamaterial technology. So you can basically have these units of design and just tessellate them, and this material itself will become a robot without having to combine all different robotic components, as in you have to do in a traditional robot. So this material itself, you just assemble them, and then they will be able to walk and being actuated, being based on their different deformation mode that you can activate by assigning different voltages. You can also assign different functionalities. For example, have a certain region of these piezoelectric metal material to be responsible for sensing. You can sense physical touch, tactile sensations, but also you can assign a focus element, piezoelectric element, to use them to emit ultrasound for sensing. So here's an example of the piezoelectric metal materials. Here's the locomotion we demonstrate. So the entire building block is a micro robot, is as small as a quarter or a penny. And they will be able to have straight motion, turning, climbing an obstacle. And remarkably, you can also do sensing. So here's a stimuli responsive micro metamaterial robot. As they walk, we have a basket that can carry, can sense a remote object being attached onto the drop on top of the metamaterials. And then you can program decision into these metamaterials. They can make a turn or immediately stop or escape. These all attributed to these dual functions of these metamaterials, being able to sense, but also being able to sense, but also being able to actuate. Okay. So next, I want to also show the capability of these metamaterials, not only sense physical touches, but also non-touch signals. For example, these metamaterials been walking here, and then they hear an obstacle ahead of them, and they will be able to make decisions to make a turning mode by emitting ultrasound. So basically kind of like bringing the sonar technology in vehicle into the micro scale. And these micro robots being walking in a straight motion. When they see an obstacle, they can actually avoid it by emitting ultrasound. So here's just the opportunities that we're showing here in ultrasonic frequency mode. But recently, we're also been working on audible frequency mode. So my student, Victor, who's current PhD student in my group, will be collaborating with Professor Karen Sabra from Georgia Tech, using these metamaterials to sense the location of sound at the audible frequency. So the example here is that you don't have to rely on a array anymore. You can just have one metamaterial and have these architecture being distributed even randomly at different angles. And then you just scan, you put the metamaterial here, and then they will be able to measure the voltage, and then you'll be able to tell the location of sound. So we developed a machine learning algorithm. You can train these metamaterials such that you get all different voltage patterns with sound coming from different directions. And then we can accurately predict the range and the distance of these objects under the water or even in the air. Okay, so I think I'm just on time, and so we still have other project going on, but with the time constraint, I won't be able to talk more about it. But of course, I would like to thank all my current major collaborators. These are our collaborators where we have currently funded project together. Professor Vikram is an expert in mechanics. Professor Jing Yin in acoustic. Professor Wei Wang and Yi Zhou from UCLA collaborating with us on graphic neural network. Professor Yaya Sami doing with gigahertz frequency, and Karen on the acoustic frequency. And of course, all my current graduate student and postdoc who I listed here, who did most of the work that I talked about today. And also our graduates, recent graduate, Xiaoyu is also a recent postdoc in my group. Now he's assistant professor of Hong Kong University. Hua Chen is now University HKUST. Ryan Hensley from Lawrence National Lab right now, and other students who have graduated working in startup and major companies, and all my sponsors who made these works possible. All right, I would like to end here and thank you for everyone for your attention, and we'll be happy to answer any questions.
Okay, great, Xiaoyu. Time control exactly, Yeah, in seconds. So proud of you. Yeah, a lot of things, you share and, I think we'll have a lot of questions to discuss. So before, that, let me first introduce our panelists. And today we have Zhang Yi. Dr. Zhang was from University of Electronic Science and Technology of China. So as a professor now, he got a degree, PhD was from Johns Hopkins, and he stayed about 10 years in Singapore and then back to China. Now he did a lot of work for 3D printing and biomedical engineering, those stuff. So today I think a lot of things to talk, in this field for the metamaterials. So we have another beautiful panelist, Pan Rui, also from Beijing University of Technology. So Dr. Pan was graduated from HIT, Harbin Institute of Technology, and he got postdoc at Tsinghua University, and now is associate professor at Beijing University of Technology. She did a lot of work, for the precision instrument manufacturing in this way. So I think today she also have many questions to discuss. And of course, welcome our challengers. At iCANX, we have this special position. Today we have Dr. Hanxiang Wu from UCLA. So actually, Xiaoyu was working at UCLA for a while. So Hanxiang was a doctor, what's got BS degree, bachelor degree from Peking University, and then go to UCLA for the doctor degrees, and now he is in the material science. And Hanxiang was a postdoc now, doing a lot of things for wearable electronics and soft materials. So welcome all of you to join on this panel. As usual, we start our question from our challenger. Hanxiang, please.
Thank you, Professor Zheng. Hi, Professor Zheng. Thank you for your impressive talks. You have introduced many interesting works based on the metamaterials. So here I have two questions. The first one is that most of your materials fabrication technologies is based on 3D printing, and both metals and dielectric materials can be printed. So my question is, what are the properties in common for the materials to be compatible with your fabrication methods?
So the first question is, what are the limitations or the requirements for the raw materials?
Yes.
Okay. So the technology platform, the one that you just mentioned, the metal dielectric material. So start with photopolymer. So it can be any photopolymer, and then you can just combine them, combine their pattern groups. So the pattern group is the group within the molecular structure of the polymer that is responsible for different electrostatic charges. So the requirements, you want to pair them with distinct charges. One pattern group that carry positive charges, other group that carry negative charges, and then you can print them. Yeah. So it's the same as any other structural polymers, but you just have to mix just a little bit of these charged polymer. Yeah. So it doesn't have to be photopolymer. You can adapt this concept into any, for example, direct ink writing techniques. Yeah, as well. But essentially, it starts with this structural material, which is the polymer. Yeah, can be photosensitive ink. It can also be other thermoplastic ink as well.
Thank you. And here comes the second question. This is a more general question. So your work is really impressive, including a vast of interdisciplinary knowledge including mechanical, electronic, materials, and also computer engineering to realize these different works. So how do you achieve this, like just by yourself or through the collaboration with other researchers?
Great question. So I throughout all my education or even my doctoral study, I always been involved in this multidisciplinary studies. My PhD topic with Professor Zheng was on building MEMS for bioapplications. So I had to pick knowledge pieces from different disciplines. So from there, I have been getting all the trainings in getting different collaborators with subject domain knowledge to collaborate and work in problem. And this, I believe that's how science and engineering needs to be done, because any societal problem that requires the collaboration of knowledge from different fields. And of course, in my current group, I attribute to all these achievements to all my graduate students and postdoc, or even undergraduate students who make all this happen. So my group comprises a vibrant combination of students with different backgrounds. So I recruit students from, for example, chemical engineering or mechanical engineering, material science, even physics or computer science engineering in my group. So it's a really nice collection of people from different skills. And that's really, I think that's really required for any modern engineering disciplines these days. Yeah. So I attribute this to all the nice collaboration between my students and also, of course, my collaborators who are domain knowledge experts in their fields to make this happen.
You must be an excellent manager for your group to, to make every student contribute their unique background.
I wish. Okay, thank you. Yeah.
Thank you, Professor Zheng. That's all of my
Okay, hi,
questions.
Xiang, you okay? Yes, all your questions?
Yes, that's all.
Okay, great. Yeah. So, of course, Xiaoyu was a great manager, a great professor to, handle all these things. Yes, now, yeah, maybe we'll go to questions. Zhang Yi, are you ready?
Yeah, I'm online here. Hi, Prof. Chen. It's really great to see you. Our entire group have been following your work, although this is the first time we meet in person, sort of. We really follow many of your work in details, and we really appreciate the new technology introduced into 3D printing functional materials. With the ability to selectively functionalize 3D structures with metals, that really help a lot to achieve functions, not just structural metamaterial, but also functional materials. And actually, we do have a lot of questions. Even just now, my students are sending me questions and ask me to ask you the questions.
Okay.
My first question is regarding the ceramic metal device you showed just now. Is the metal sintered together with the ceramic?
Yeah, so everything needs to be centered. So those are the results that one structure is post-sintering.
So metal is deposited post the ceramic sintering. Is that what you mean? Before.
Yeah, before, and then you sinter everything together. Yeah.
Oh, and what temperature, may I know?
So sintering temperature really depends on the type of ceramic. So the one that we use, I would say just right above 1000 degrees.
And that won't destroy the metal layer on top?
No, yeah.
Oh, okay. All right, my another questions are regarding all the structures you printed. Many of them look very complicated. Don't they need support structures during printing?
Most of them don't. A lot of architectures, if you look at them, they're self-supporting. So, so you can have this algorithm, right? Before 3D printing, build a CAD model. A lot of algorithm can tell you whether you need supports. If there are structures that may need supports, you will immediately notice. And then we also have a technique. You can actually add a dissolvable material as the support. Dissolvable material I also been using not directly writing, like FDM or even some SLA technique or material jetting technique. So you just add a second phase of material as a dissolvable material as the support structure, and then put into etching solution. Yeah. and the
I see.
superconductor will be dissolved. So that would be the way to do that. There's a mechanical way would be you may have to cut the supports, but for complex metamaterials, it will not be possible. So
I see.
we have a work published in the additive manufacturing journal that documents. Yeah. So adding a dissolvable polymer, you can get virtually any type of architecture.
Yeah, we're definitely looking into that. Thank you very much for the answer. And another question is regarding your piezoelectric structures.
Yeah.
You mentioned you can almost design any kind of a piezo tensor in such a complex structure, but how do you do the polarization if all the tensors are in different directions?
So the polarization you can do two ways, right? So most of the one that we showed are polarized in a uniform direction. So
Okay.
yeah. So you just put the lattice in two electrodes and then you pull them. Yeah. You could also do that because we can also have this electrode to be mounted on each individual ligament.
Mm-hmm.
You can also do in situ polymerization polling at each section of the metamaterial. So that gives you an additional design dimension to design. Yeah.
I see.
You
I
can do
see.
in situ polling as well. Yeah. Yeah.
I
But for the
see.
most work that we demonstrate is just uniform polarization. Yeah.
Okay.
In situ is
Sorry.
polling.
Yeah, I mean polling, not polarization. In that case,
Yeah.
you mean even the polling is done in a uniform field, and the structure created can still accomplish the piezo tensor in all different directions?
Yeah. So because that's really the magic, the beauty of metamaterial is that these deformation, right? So although the charges are being distributed in one direction, right?
Mm-hmm.
The dipole being this, but the deformation is achieved by the angle and orientation of the stress. So that once they deform, this local stress will either contract and relax, but based on the topology they are in, they can give you a net force.
Okay.
Yeah. So net
Okay,
force
I
based
see.
on is a purely a topological effect. So I give you the net force of like a twisting or or shearing.
I see.
Basically, it's the structural design that allows you that even though those the dipole are in one direction, but the net deformation will in other directions.
I
Yeah.
see.
We take that inspiration from earlier work from people doing mechanical metamaterial. For example, if you compress a solid, architecture solid, the solid usually for continuum material, they will either shrink, right? They will shrink, relax when you compress them. But from the structural design inside, they can twist. Yeah, or they can shear. So that's from the topological effect. So we inspired from that concept, and then we adopt them into these electromechanical. Yeah.
I see. I
That's
see.
where, yeah, we basically look at the inspiration from this mechanical material. Yeah.
I see.
Yeah, to do
In
that.
that case, would it be in situ polling be more effective if the polling is done along the lattice direction?
I would say that's just a different control, right?
Mm.
So if you don't do any structural design, right? If you just, let's say, design a topology, a regular topology, for example, like a wood pile structure, I could imagine if you pull them locally in different directions, you can probably also achieve some very interesting deformation.
But that will be more difficult, I imagine.
That'd be a lot more difficult. Yeah. So I would say that's the beauty of metamaterial is that you can just design any topology to achieve the deformation you want without having to do complex device assembly.
Yeah,
Right?
definitely agree.
Yeah. So in the piezoelectric device domain, expert they use these in situ polling. You just talk about what they do is they pull this disc. They can mount these piezo disc, layers. You can pull them horizontally, right? So one layer you pull them in this angle, other you pull them in that angle. You can do that too. Yeah.
I see. I see. Okay. My last question is kind of more general question, not technical question. So I wonder, what's your take on the sort of large scale production of metamaterial? What's the biggest hurdle for it to become a real world application before
Yeah,
metamaterial?
so talk about mechanical metamaterial or more like a functional. It really depends on the type.
I would say functional.
Okay, so let me just first give you a structural metamaterial as an example, right? Structural material, people will talk about, okay, can you make it larger, right? How large? So I would say that's limited by the fabrication. 3D printing, I believe Professor Joseph Dieselman talked about roll to roll, right? You can make large quantity of them, but they're limited by the Z height, right? You can make really small structures with roll to roll, but for 3D it's still difficult to make them really tall in a time efficient manner. So most additive manufacturers struggle with the smallest feature size you can do versus the large scale, right? So you can optimize, design your machine actuators or programming the optics motion to optimize the speed, but eventually it's limited by the resolution and the build size of the actuator of the platform. Yeah. So we've achieved up to a meter level. Yeah, 50 centimeter up to a meter level. But you just basically scale up the stage in optics. Yeah, design optics such that they don't really deform or cause severe aberration when you move the optics in large dimension. Yeah, so it's limited by machine. And secondly, when you talk about the behavior, so that's why we're studying these fracture toughness, right? We're talking about, okay, so if you have this unit cell being a few microns or tens of microns, replicate them 10 million cells. Is that good or bad? So my collaborator, Vikram Deshpande, has shows that if you really want to take advantage of these mechanical metamaterial behavior, you actually don't want to have these tens of millions of unit cells. So it basically shows the limitations. If you have more than 10 million unit cells, these metamaterial will actually behave as a continuum materials. And then you actually lose a lot of those benefits from those exotic structures. Yeah. So you want to have unit cell to be lower than 10 millions, so that the size of the unit cell can be comparable to the overall size of the metamaterial. So this is a little counterintuitive because people want to make them to behave as a continuum material, but you don't want to have too many unit cells in them. Yeah. So that's the kind of fracture behavior that we've been studying. That's quite interesting. Yeah. For functional material, I would say actually being able to make them small is a great thing. So we're not only, so indeed, we're not really looking at making them large. We're trying to make them small. Yeah. So because electronic devices, you really want to, breaking Moore's law, you want to, if you really go to small device level, you want to shrink the size of these material. I do see that's kind of a limitation and opportunity that we're working at to really shrink the volume or feature size of these functional materials and resolution. Yeah, because you want a spatial resolution for electronic devices. Yeah.
Yeah. Thank you. Thank you very much. It's really eye-opening.
Thanks.
Very insightful discussion. Yeah. So Pan Rui, are you ready? Yeah.
Yeah. Thank you,
Please.
Professor Zhang. Yeah. Professor Zheng, thank you for sharing your very interesting research about the metamaterial. It's very fascinating. So since Professor Zhang has asked several questions that I am also interested in, so I have one general question though. So you mentioned that there is no systematic principles to design metamaterials, right? So is there any other technicals that you think may promote the development of metamaterials, maybe including not only design, but also fabrication technicals?
We're talking about design method, right? So there are basically three categories of design. The first is the analytical design approach. That has been in the literature for over 50 years, right? It's basically it's kind of like mechanical design to design a topology. And we still use that. In fact, the paper, the piezoelectric measurement was designed by analytical approaches. Yeah. Get inspired by chirality, by stretch-dominated architecture. Basically, you can do that by classifying the deformation mode of metamaterial. You basically have to study the topology, or which topology, which angle or pattern will give you certain deformation. So that will give you a general idea of the design philosophy or trend, and then you go doing computation to design, okay, what are the stress diameter, what are the angle you need. But first you want to have these classification to choose the right building blocks. So this is the current analytical approach, and I still use it. I think that's actually one of the fastest. Yeah. But now, you know, everything you wanted to computerize, right? You want to achieve ultimate design. Then the second powerful one is also being very popular over the past 30 years, is a topology optimization. So basically, you can define a mesh. Basically, it's a solid, right? And then you really have to decide, okay, inside of that solid, where I need to be a solid material, which area I need to be the air, right? To use topology optimization to optimize the quantity. Yeah, for example, give me a design that can maximize the stiffness at this particular weight density, then you use topology. So there's commercial software to do that, and it can allows you to fit any architecture into any curved surfaces. People use that to design like shoe midsole, wearables. But the problem with topology optimization is that if you want to try to optimize those nonlinear behaviors, it's been very challenging, because nonlinear behavior to simulate them really takes ridiculously long time to do that. So now recently, with these artificial intelligence, right, machine learning. So my group, along with several other groups, are working on developing machine learning technology, so that you just need to train large amount of data. Yeah, it's still basically the time-consuming part is from the training process. But once the training is complete, you can virtually design any topology, and then the design process will only take a few seconds. Yeah, and that gives you any nonlinear behavior. But you still have to train them. So training is basically I would say the novelty comes from the training process. What are the representation method that you can use to relate metamaterial, which is solid physical structure, to the virtual space? Here we use these graphic neural network, graph model. And there are other approaches. You could also use possibly large language model. I've seen some work doing that, or just traditional classification decision tree based method. Based on what I just mentioned, like you classify different topology, you make a library, and each library, each unit cell type can serve as a gene, and then you just train them. Yeah. So I would say these are the three approaches that I would use based on different applications, based on the needs to do that. Yeah, I think that's the three major techniques.
Yeah, very enlightening. Thank you. So I may have one more question though. So I don't know whether you encounter any challenges when you fabricate all these metamaterials. So my question is, what do you think are the limitations and also opportunities that you think for developing the fabrication techniques of metamaterials?
Yeah, so that's a great question. So this is something, you know, for any new device that we struggle from day one. Let me just give you a piezoelectric material. So I first got excited by piezo by just reading some magazine. Okay, so this professor synthesized the piezo powders. They can achieve such high quality. And really, I read that and said, okay, why can't we combine these powders with these photosensitive monomer, and maybe we can print them? So then I talked to my student, Xiaoyu, who's my first PhD student, along with Rayne and Xiaoyu. So we basically mix these powders with this polymer. And then we try printing, you know, for months, I think for over a year, there's no problem at all. So no matter, say you mix this low quantity and then print them, you get beautiful structure, but there's no charges generated. So then we have to look at collaborators, and then we figure out a way to actually do a surface functionalization to functionalize these nanoparticles with these on the surface of nanoparticles, so that they can have a covalent bonding with this polymer. then we immediately saw very good piezoelectric model. So challenges come from first the feedstock material, right? How can you get high quality functional materials, and how do they interact with a 3D printable blender? Yeah, is the key. And we're also working on commercialization effort, and for commercialization and eventually use the mass production, it comes to currently these are being fabricated by benchtop, lab facilities that we build, custom build these multi-material printer. You certainly have different failure rate, right? So eventually it will come from machine design and automation to have more defect-free or streamlined technology. For example, Joseph, this amount demonstrated is a roll-to-roll technique, right? So what we are thinking is more like the incorporating automation or more efficient mechanical system, electronic system to achieve a more high quality fabrication. Yeah. So everything from fabrication to deposition, the eventual quality control from the industry level, which is, how do you automate them? How do you do the quality control? Yeah. That's what I would say more down the road of commercialization effort. That's not something we are too worried about during the lab phase.
Okay, this is very brilliant. Thank you.
Thanks.
Super, super. Actually, Xiaoyu, you mentioned that you already gone to the commercialize, the step. So yeah. So what's the big challenge you're facing?
Yeah, for any commercialization, you just have to find the right applications. Yeah. And that has to be done with the right customers and build cases or collaborators that you can have. Yeah, I would say the right customer, the right collaboration, and to tap into the right field. Yeah. For example, one that we've been working on, which is the stent. So we found a great collaborator who can actually do animal testings, and they're the expert in making stent and do bioimplantable devices and look at how they interact with the blood clot. Yeah. So
does this need a FDA, kind of approve or something? Oh, no,
yeah, for long term you'll do that. Yeah, yeah. But first they are doing the animal test. We're looking at them, let's say, for put them in the mice for a month and see how they behave. Yeah. So that we're still in that research phase. Yeah. For this.
Okay, super. Yeah, that's really, really great. Maybe I have another questions for you, Xiaoyu. I know you stay in this field for a long time, really contribute continuously, Yeah, so in the last more than 10 years. So like Zhang Yi says that they all follow your work. So what's your perspective, for this field?
Oh, for that, so this metamaterial is always an active field. It's very broad because metamaterial basically is how material interact with the physical world. And when we describe the physical, we just use one quantity, which is the wavelength. The wavelength of the forces, right? If the wavelength is a hertz, right? Below 1 hertz, that's just like you can think of the quasi-static forces. That's the mechanical metamaterials, right? If you just increase the frequency, then it's an audible metamaterial for noise cancellation. Then if you keep increasing ultrasonic metamaterial, and then you keep doing that, which is the terahertz metamaterial, that is also a very exciting field. It is not my domain, but I also recently, because we can also look at how metamaterial interact with gigahertz wave. Yeah. So I think we're still pushing the boundary. It really depends on different applications and how do you marry with certain different applications, whether it's about medical applications or structural or electronic application. I think it's a really great opportunity that you can see this continuing growing the next, I would say, 50 years at least. Yeah. Yeah,
okay. Yeah, it's interesting because Jill in the last week was talking on the stage as for his roll-to-roll, really mass production for millions. So we have a nickname for him is Juan Wang, the king of roll-to-roll. So yeah, I'm thinking of, maybe I can, you are the king of the smart metal material in the future. Congratulations. Yeah, really looking forward, to have more and more kind of stuff to come out in this field, and really looking forward to getting in the real application, as
Yeah.
you mentioned that this was a key point. If a
Yeah.
field want to grow and get more attention, get, active, they must find the real market, right?
Yeah, there's been many real applications from antenna. One example, acoustic cloaking devices, acoustic metamaterial, meta surface, meta lens. Yeah, there's already people pushing all different applications. Yeah.
Okay, thank you. Yeah, thank you for your great questions and answers. Thank you for all the panels. Now I'm going to share my screen. Did everyone see my screen? Yeah. Okay. Xiaoyu, you can see my screen, right? Yeah.
Yeah. See it.
Okay, now, yeah, I'm glad to say that I can, distribute this e-certification to you. Actually, I say that if you did the speech, good, answer question right, I will deliver this to you. So proud of you, yeah. All questions didn't, challenge you, yeah. So, very, very proud of you. I really, put more attention on this, intelligent metal materials. I think, have a really bright future. So Xiaoyu, thank you very much for you, really early in California, 5 o'clock or even 4 o'clock. So such a, very energetic inspiration, talks. Congratulations and thank you very much.
Thank you so much for having me. Glad I didn't fail the question, so I can have the certificate.
Okay, super. Actually, we're going to have a big event, of iCANX. This was the first years, for this online talks. So we will first go together, in Davos this July and summer. So in Switzerland, so we will have a big, iCANX Davos summit. I hope we can have all of you, to go there to, for these discussions in the science, technology, innovations, investment management, entrepreneurship. So it will be a big go together. So it's time to think about it. It's time to go there. For the impersonal, kind of activities, events, and more high events will be there. So welcome all of you. And next week we're going to have the 4th year's anniversary, and we also have a super young, stars on this stage. Xinge Yu from City University of Hong Kong. So I'll talk about intelligent soft electronics. And yeah, a big panels, of course, for next week, like this, hard topics discussions. So welcome to follow iCANX, on the stage. And I see you next week and enjoy. Okay, yeah. Hello, ladies and gentlemen, my dear friends. Welcome to iCANX Davos Summit. So this year we're going to have this big event in Davos, Switzerland. We have 6 topics: innovation, science, technology, investment management, entrepreneurship. Short for it's time. So it's time for us to go together. It's time for us to all these inspiring talks for the future. We'll have a Nobel laureate firms. We'll have president of academic firms. We'll have president of university firms. All these big names will be here to talk about the future, what's going on for the future. We also invited all these world leaders, scientists, investment management to go together to talk about, what technology and science going to be for the future. And we're going to listen to many sharp talks. All these great figures was from each field. They will share the sharp ideas, the latest results. So it's not only a platform for all these big names, for these shining stars. We also invite you to share your stories. So it's time for you to deliver a talk here. So you are welcome to submit your materials online. So we have many sub-sessions, parallel sessions. You are welcome to submit your materials, and we're going to pick up someone to share that. And it's our time also invite you to be superstars on the stage. If you are college students, welcome to apply for Innovation Award. If you are young scientists, welcome to apply Young Scientist Award. If you already have your startup, welcome to our Startup Award. All these applications is due April 1st, so you have about months to submit it. And it's time for us to go together. We have all these people here who want to work together with you. So we from different continentals, different countries, different areas. So welcome to join us, and it's our time to go to Davos. Now the pre-registration is open now. You are welcome to submit online and go summit together.
汽车电子化的迅猛发展正在掀起一场技术革新的浪潮。集万千期待于一身的电子元器件，必须以更高的技术水平和可靠性，为汽车电子化提供支持。多层陶瓷电容器、电感器、高可靠性元器件，太阳诱电挺身而出，肩负起推动未来科技进步的重任。电子元器件的发展与汽车、工业设备和网络时代的发展密切相关。为此，太阳诱电开始了充满激情的挑战。心怀梦想，无畏挫折，不懈奋斗，为用户、为未来高新技术领域倾力打造、倾情奉献优质的电子元器件。太阳诱电将吸引全世界的目光。
先生、女士们、亲爱的朋友们，欢迎大家来参加我们的 iCANX 达沃斯科学峰会。那今年是第1